Hello and welcome back. My name is Dr. Mark Taylor, and this is the second of a series of videos reviewing the Delaware Tech Physics 111 Exam 3 Preparation and Practice Exam on Waves and Sound. And we're going to continue with showing you how to draw transverse and longitudinal waves and to include some of the structural elements of those waves when you draw them. Question number 5 says, draw a typical transverse wave as a displacement versus length graphs. In other words, it's versus length or distance as opposed to being versus time. Remember, these waves are constantly moving, and when you draw them, you can either draw them as a snapshot in time, which would be versus length, or you could show them as how a single point in the wave would change over time, and both of those would look like transverse waves. So let's draw them here. We have our equilibrium position in the center. We have some displacement axis. Then we just draw the wave showing crests and troughs. There's a crest, trough, a crest, a trough, crest, etc. So it says label all the crests and troughs. There's a crest. There's a crest, there's a crest. The crests are the peaks. The troughs are the valleys. Trough and trough. And if I had continued on, I would have hit another trough. So now we have an even number, but you don't need to have an even number as long as they're alternating. It says label one amplitude. So the amplitude is the displacement between the equilibrium position and the farthest it can go, and that would either be to the top of a crest or to the bottom of a trough. So we give a simplified definition of amplitude as the height of the crest or the depth of a trough in a transverse wave. Either one of these represents a single amplitude. Remember, the amplitude is not the full width. That would be twice the amplitude. And a wavelength can only be observed on a diagram of when you draw a wave versus length. In other words, this axis here is our length axis. It's our distance or length. It's in meters or centimeters or some length unit. And the length between two adjacent crests, the length between two adjacent crests is a wavelength. Or the length between two adjacent troughs is a wavelength, or the length between two identical points that repeat anywhere on the wave as long as they are the adjacent one. Pick a random point in the wave and look for the next identical point because this is a repeating structure, and that is also an example of a wavelength. But the easiest way is to go from crest to adjacent crest or trough to adjacent trough. The next problem, number 6, says draw a typical transverse wave. Well, that's what we just did, but this time it's as a displacement versus time. So it's going to look exactly the same, and we'll just draw it the same way. I'll do this one in blue. And you have the crests and the troughs alternating. I'll label one crest and one trough. And it says label an amplitude. Well, we know that that's an amplitude. And we know that that's an amplitude. Amplitude doesn't change whether it's versus length graph or versus time graph. The thing that does change, however, is if you were to measure from crest to crest, remember, this is a time graph, so this axis might be in seconds, it might be in milliseconds, might be in nanoseconds, femtoseconds, some time unit. Now, any change from one crest to another is not a length anymore. It's a time, and this specific time is the time it takes one cycle of the wave to pass by a given point. So you can imagine this wave is moving with time, and this is a point, and then this point goes down, and then it goes back up, and by the time it goes back up to the same crest position, that time is called the period, and we abbreviate that with a capital T because it's a special type of time. That is, the period, T, is the amount of time for one cycle, one up and down or one down and up. And the beauty of being able to get period from a graph is that once you have that value, T, you can do a simple calculation to calculate frequency. 1 over T is frequency. And it's important to remember that because that will come in handy when you start doing wave calculations. And the last question on this page is draw a longitudinal wave as a displacement versus length graph. Now there are several ways to represent a longitudinal wave. Remember, a longitudinal wave is a series of alternating compressions and rarefactions of atoms or molecules, and this requires you to draw a lot of dots. So it'll look something like this, and that grouping of dots would represent your first compression, and we'll come back to the rarefaction, but here's the second group of compression dots, and a third, and one more. Now we'll fill the spaces between the compressions with many fewer dots to represent the spreading of the rarefactions. So this would be a representation of a longitudinal wave, and you can see that it's very time consuming to draw. And you can certainly draw it this way, and it's probably the most accurate representation of a longitudinal wave, but you could also draw it in certain shorthand ways. One relatively quick way would be to represent the compressions with a series of tightly packed vertical lines. Show it like this. And the rarefactions in between would be just represented with sparser lines, just fewer lines. So here you see a representation of a longitudinal wave where lines are very closely packed together representing the compressions, and lines are spread apart representing the rarefactions. And a third way to draw this, and it's really up to you which way you prefer, is to simply make a slinky with tight springs in the locations where the compressions are at and loose springs where the rarefactions are at. So it'll look something like this. And if you look at the curls of the slinky shown in black here, you can see tight curls where the compressions are and open curls where the rarefactions are. So any one of these three ways is perfectly fine on an exam if you're asked to draw a longitudinal wave. Now, how do we analyze this wave? Well, first we're asked to label all compressions and all rarefactions. Well, our compressions are here, and here, here, and here. So the rarefactions are just the spaces between the compressions. Here, 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 and there's a piece of a rarefaction out here. So I'll label all the compressions C, and all the rarefactions R. And lastly, for this problem, you're asked to label one wavelength. Well, since this is a plot versus length as opposed to time, we can get the wavelength from this. If it was against time, we would be able to get the period from it. So how do you get the wavelength? Well, this doesn't look anything like a transverse wave where we have crests and troughs. Here we have these compressions of particles and then rarefactions of particles spreading out of particles. What do? Well, in this case, you merely take the center of a compression to the center of the next compression. And the wavelength is the distance between these two. And of course, you could always take the distance between the center of a rarefaction and the center of the next rarefaction. But it's probably easier to find it between compressions. Okay, let's take a look at the next page. So we're going to continue talking about wave types, features, and properties. So number 8 says provide at least one example of each type of wave. A and B are mechanical and non-mechanical waves, and C and D are transverse and longitudinal waves, and then E is combined problem for both mechanical and longitudinal waves, so it has to be both. So mechanical waves, these are waves that absolutely require matter. This is going to be any sound wave, any pressure wave of any type, any water wave of any kind, and any seismic wave of any kind. All of these require matter for the wave to travel through. Sound can travel through any kind of matter. We're used to hearing sound through the air, but sound can travel through any kind of matter. It can't travel through vacuum. Pressure waves are typically what we refer to waves that are going through liquids, sometimes solids. Water waves obviously go through water, and seismic waves obviously go through the earth, and the earth has both solid layers and liquid layers. All of these are waves that require matter, so they're all mechanical waves. Non-mechanical waves, these are waves that do not require matter to go through. They could go through matter, but they do not require matter. Okay, this would be all electromagnetic waves, also known as light waves. And these are not just the light waves that we can see with our eyes. It's all kinds of light. So that could be radio waves. I know we don't think of those as light, but they are. Microwaves, infrared, visible, those are the ones we can see, ultraviolet, X-rays, and gamma rays. Squeeze that in here, right? But another type of non-mechanical wave that we don't cover in this course are gravitational waves. They are also non-mechanical waves. They do not require matter to go through. I'm just giving you another example of non-mechanical waves that you could write down as an example. Transverse waves. Well, it turns out that all EM waves and all gravitational waves are transverse waves as well. So we can put all EM or light, and you could name any one of these specific types. That would still be a reasonable example. All EM waves and gravitational waves. Those are all transverse waves. But there are some other mechanical waves that are also transverse waves. For example, S seismic waves. This is a specific type of wave that actually has that transverse shape to it. And another example would be surface water waves. These are the waves that are the result of water at the top of the surface of water, the ocean, sometimes lakes, that's moving in a wave-like manner. So different layers of the water have different patterns of how their wave is moving, but at the top of the surface of water, they have that classic transverse wave shape. Next, we have longitudinal waves. And for your purposes, the most important longitudinal wave to know is the sound wave. Sound waves are longitudinal waves. Now, I'm going to say that, but you'll notice a lot of times when we analyze sound waves, they look like transverse waves. Now, please don't confuse these with the actual sound wave. These are waves that are artificially created from the original sound wave in order to make the analysis easier. But sound waves are longitudinal waves. Make no mistake about it, they are examples of longitudinal waves, as are any kind of pressure wave, and specifically one type of seismic wave called the P seismic wave. Now, I just mentioned the S seismic wave and the P seismic wave. The P and S actually stand for primary and secondary. They refer to how fast these waves show up when an earthquake happens. But you can think of the P seismic wave, because it's longitudinal, as being a pressure wave. And you can think of the S seismic wave as having an S, just like the word transverse, which has two S's in it. So that might help make it a little easier to remember. A mechanical longitudinal wave, so it has to be a longitudinal wave that is also mechanical. Well, it turns out that all longitudinal waves are mechanical. Not all mechanical are longitudinal, but all longitudinal are mechanical. So that would be sound again. It's the same list. Pressure waves, and specifically the P seismic wave. All right, our next problem says, for each wave property listed below, label whether this is a property of transverse waves with a TR, longitudinal waves with an LO, or both. We have wavelength, whose symbol is a lambda, the Greek letter for the lowercase l, frequency, lowercase f, period, an uppercase T, amplitude, an uppercase A, and speed, a lowercase v. And I'm going to make this easy for you. Every type of wave has every one of these properties. All waves have wavelength, frequency, period, amplitude, and speed. Now, these properties tend to be much easier to analyze on transverse waves than on longitudinal waves, but all kinds of waves have all of these properties. So that really makes things simple here. They're all both. And the last question on this page says, order the media for how fast sound travels in each, from fastest to slowest. And we have 5 substances that sound might travel through: air, rubber, rock, vacuum, and milk. And you'll notice some of these are solids, liquids, gases, or vacuum. And what we know about sound is sound prefers to move through the densest material, even more accurately, the stiffest material. It will always move faster. And by far, the stiffest material is rock. And so it will go the fastest through rock. Well, let's jump to the slowest. We have air, rubber, rock we already talked about, vacuum, and milk. Well, vacuum has no matter at all. Sound is a mechanical wave. Why is it a mechanical wave? Because sound travels by transferring its energy from one atom or molecule to the next, to the next, to the next, to the next. So if a vacuum is present, there's no matter to oscillate, to vibrate, and therefore energy can't be transferred and the sound wave can't propagate. So a sound wave cannot travel through vacuum. The speed of sound in a vacuum is 0. There is no sound in a vacuum. There is no sound in deep space where there is no matter. The amount of matter there is so negligible, sound cannot travel. So if you see a science fiction film with a giant explosion in space and you hear a loud boom, that's essentially nonsense, because in space there is no sound. Maybe on the space station, maybe on the rocket ship, they would hear some sound, but in space, it's a vacuum, there is no sound. So we're going to put D here as the slowest. Well, how do we fill in the rest? Well, rock is a stiff solid, but we also have a flexible solid. That would be our next fastest medium for sound to travel through. Those are our 2 solids. We'll look for a liquid. Well, we have milk. Milk would be next. It's our only liquid in the list. And then we're down to air, our only gas on the list. So the order is going to be rock, rubber, milk, air, and then no sound in a vacuum. And that completes this video.